Hello, we are starting graphing rational functions today, the last part of our rational function content. So you are going to need a calculator for this, so if you don't have yours handy, go ahead and pause this and go grab it. The first thing we are going to do is use our table and practice using our table to find out information about what our graph of one of our rational functions would look like. So starting with this first mini example here, we want to first find our domain. Now, domain would be something that either gives us a negative inside of a square root or gives us a 0 in the denominator. In this case, if x were equal to 1, we would end up with 0 in our denominator. So our domain would be all values except for positive 1. So what we want to take a look at is what is our graph doing close to the value of 1? Because obviously if we plug in the number 1, we're going to get a non-existent function. You get an error in your calculator, it doesn't work. So what is our graph doing like slightly before and slightly after the number 1? And that's where we use our table. So the first thing you're going to do is go to your y equals menu, and you are going to go ahead and type in this function, making sure to protect your numerator and your denominator by parentheses. Okay. Then you need to go to your table set, and you need to make sure that your independent variable is set to ask and not auto. So if you just arrow over and hit enter, it will change that for you. Then we're going to go to our table, and I'm going to delete the values that are currently there. And we're going to first start by doing this table at the top here. So you're going to type in these x values. So 0, 0.5, 0.9, 0.99, 0.999. So we're getting from 0 closer and closer to the number 1. And if we look at these y values, they are getting bigger in the negative direction. So they're going towards negative infinity. So that's between 0 and 1. Now, the next table is going to be looking at values bigger than 1 getting close to 1. So you can either hit the delete button to clear what's already in there, or you can type over these values in your table to replace them. And so on the other side of 1, they're getting bigger and bigger positively. So between 0 and 1, and obviously smaller numbers, we're going off to negative infinity. On the other side of the big numbers that are bigger than 1, we are going off to positive infinity. Now the last thing we're going to look at is what's happening as x goes off to positive infinity. So as x gets bigger and bigger, what is happening to our y values? And they're getting very, very small, and they're getting closer and closer to the number 2. So what we have here are boundaries on our graph, and we call those asymptotes. They're these invisible lines that our graph gets close to but never crosses. So our vertical asymptote would be those x values that it could not be, which was 1. So x equals 1 was our vertical boundary for this graph. And our horizontal boundary would be y equals 2, that number that it's getting really, really close to, but it's never quite touching. So that's what our vertical and horizontal asymptotes tell us. They tell us the boundaries of our graph. Now, how do we determine what they are? Our vertical asymptotes have to do with our domain of our function. So in this first example that we're going to talk about here, the first thing we want to do is factor. So if I factor my numerator and my denominator, I'll see that in my denominator, the values positive 3 and negative 2, I'm sorry for that bell. I was saying the values positive 3 or negative 2 would give us a 0 in our denominator, so they're excluded from our domain. X cannot be those numbers. Now, if I look at what I have factored, I have a common factor of x plus 2 that I can simplify. This is called a removable discontinuity, or RD. That's the removable discontinuity. I can cancel my common factor x plus 2 to get that removable discontinuity, and what that's going to end up being is an open circle or a hole in our graph. So negative 2 is the x value. You find the y value by plugging in negative 2 to your now simplified function. So after I've canceled those x plus 2's, here's my simplified function, and if I plug negative 2 in here, I'm going to get negative 21 over 5. So here's my removable discontinuity. It's an open circle on our graph. And what that leaves us with our domain exclusions is just -3, and that becomes my vertical asymptote. So your vertical asymptotes, you are going to factor, identify your exclusions. If there's a removable discontinuity, you identify that. If there's not a removable discontinuity, all of these exclusions, however many you have, 2, 3, 4, are your vertical asymptotes. So it is possible to have more than one. Then your horizontal asymptotes follow 3 rules. And these rules have to do with the degree of your expression, which is the largest exponent. So for example, x cubed, that largest exponent is 3, so that would mean your degree is 3. X squared, your degree is 2. So it's looking at, in your numerator and denominator, what is the largest exponent present, and that is the degree. So if your higher degree is on the bottom, then your horizontal asymptote will be at 0, no matter what. If your higher degree is on the top, then you have no horizontal asymptote. And if they're the same in the top and the bottom, then you divide their leading coefficients. And the little mnemonic device that we use to remind ourselves of these is Bobo Botten eats DC. So bigger on bottom, your horizontal asymptote is 0. Bigger on top, you have no horizontal asymptote. If the exponents are the same, then you divide the coefficients. Okay, so that's the Bobo Botten eats DC. Now going back to that same example we just talked about for the vertical asymptotes, my degree on the top is 3, my degree on the bottom is 2. It's higher on the top, bigger on top, so this would be Botten, bigger on top, so we have no horizontal asymptote. So what does all this information help us with? Well, if we're going to graph one of these rational functions, first we plot our vertical and horizontal asymptotes with dotted lines. If we have a removable discontinuity, we put that with an open circle. And then we use a table to figure out where our graph exists on and around these barriers with our asymptotes, and you connect the dots to sketch the graph. So let's go ahead and practice this. We're going to do 2 examples, starting with example A. The first thing we need to do is identify our domain. So I'm going to factor my function. In my top, I have a difference of squares, and in the bottom, that's x plus 3 times x minus 1. So my domain, what values would cause this to be 0? Well, if x was -3, or if x was +1, that would give me a 0 in my denominator, so those are my domain exclusions. They cannot be part of my domain. But I do have a common factor, this x minus 1 and x minus 1. That means that this 1 is going to be my removable discontinuity. So my simplified function, after I cancel the x minus 1's, is x plus 1 over x plus 3. So my removable discontinuity is 1, and I find the y value by plugging in 1 to that function. So 1 plus 1 over 1 plus 3, that's 2 over 4, or 1/2. So there's our removable discontinuity. That's going to be an open circle on our graph. Okay. So that became a removable discontinuity, which means our remaining domain exclusion is -3, and that becomes my vertical asymptote. So x equals -3. Now we're ready to move on to our horizontal asymptote, which means we're going to look at our Bobo Botten rules. So you can look at the simplified or the original function. Either way, the degree is the same, 2 and 2 or 1 and 1. So our horizontal asymptote is going to be the dividing the leading coefficients. So the leading coefficient here is 1 and 1, or the same thing, 1 and 1. 1 divided by 1 is 1. So that means our horizontal asymptote is at y equals 1. So I am going to use dotted lines for my asymptotes, vertical at x equals -3, horizontal at y equals 1. And I have an open circle at my removable discontinuity, 1, 1/2. So I am going to put my open circle there. Now I need to figure out what my graph is doing in other places on this graph. So if we kind of split this up, I've got the left side of my barrier, and I've got the right side of my barrier. What I'm going to do now is use my table to figure out what's going on in both of those sides. So let's look at our left side first, this yellow side. what x values exist in my yellow portion of my graph? Well, I've got like -10. We could skip a few up to -6. But basically, where it's going to be hitting a wall is when it gets to -3. So what I want to do is find values that are close to -3 but don't quite equal -3, because if I put in -3, I'm going to get an error. So we could do like -3.1, -3.01, -3.001. Essentially, we just want the table to give us an idea of what is going on with our graph. So we are going to go back to our y equals menu and put in our new function, our simplified function of x plus 1 divided by x plus 3, again protecting it with parentheses. And if I go to my table, I'm going to get these values. So they are positive, and they are getting bigger as it's approaching that -3 boundary. So what that's going to look like, and this doesn't have to be super precise, but basically they're tiny numbers, and then they're going to jet off to be super large positive numbers. But they're all positive, so they need to be in the positive y section of your graph. So now we're going to repeat the same thing for the green side of our graph. And based on where our hole is, you should be able to guess where exactly this graph should lie, more or less. So looking in the green area, some values that I'm going to have here. Well, 10, obviously. I can skip a few. Let's go with 6, maybe 2, 0, -1. And again, we're going to be hitting this boundary at -3. So we want to find values that are close but don't equal -3. So like -2.99, -2.9, and so on. So now I'm going to put these values into my table. And again, we've got tiny positive numbers. And then we end up with really large negative numbers. So it's going to be close to this horizontal asymptote. It's going to touch my open circle. It goes to the point -1, 0, so you can point that, just plot that point just for accuracy. And then it's been going off to -infinity. And so there are both sides of my graph. Okay, and again, doesn't need to be super precise. I just need to see that you understand these are positive values, and these start off as small positive values, and then it goes to -infinity, and you've got that open circle there. All right, looking on now at example B, the first thing we need to do is identify our domain, and we do that by factoring. So in the bottom, that is a difference of squares, so I can factor that. And my domain exclusions would be that x can't be +2 or -2. And neither of these are going to be able to simplify with what's in my numerator, so I am not going to have a removable discontinuity this time, which means both of these are my vertical asymptotes. I'm going to have 2. Okay. Then for my horizontal asymptote, we use our Bobo-Botten. It's bigger on the bottom. I've got x squared on the bottom. So bigger on bottom means that it is 0. So our horizontal asymptote is going to be at y equals 0. So I'm going to go ahead and plot our 3 asymptotes, our 2 vertical at 2 and -2, and our horizontal one at 0. And I am going to get cut off for time on this video, so I'm going to continue in part 2.